Good afternoon all. Welcome to the last and most interesting talk of the exciting Samvaad series on cryptography and security. As you all know, the speaker of the day is Dr. Ashish Choudhury. So Dr. Ashish Choudhury is an associate professor at IIIT-Bangalore, where he previously held the position of Infosys Foundation Chair Professor. He did his master's and PhD from IIT Madras and postdocs from ISI Kolkata and University of Bristol. His current research interests include privacy-preserving ML and efficient consensus protocols. I, on behalf of the IIIT research community, welcome him to share his insights. Welcome, sir.
So thanks for the introduction. So what's the plan for the talk? If you see the picture here, this is not Rohit Sharma hitting a six. That's how I view Professor Bhavna kickstarting the thematic talk series regarding crypto, because it was really a talk with a bang. She very nicely introduced what exactly cryptography is all about. And then the talk was followed by a couple of very interesting talks on a broad theme of cryptography and security. We had Professor Srinivas Vivek talking about his research, which actually triggered a collaborative work including me. That means Samvaad really has some impact in terms of inciting interest research. And the talk was followed by another interesting talk on blockchain technology by Professor Tricha and her students. So that means now, since this is the last talk, I have tremendous pressure on me. I have to really end the talk, thematic talk series with a bang. So what I will do is I will take motivation from Captain Cool Thala, and I will try my level best to indeed create an impact regarding this crypto-related talk series. What's the roadmap for the talk? We have 3 parts here. I don't know how I will be able to manage the time. So it's like test match, one day international and 2020. Part 1 will be a very generic, very general, gentle introduction to what exactly is Byzantine Agreement all about, some known results. Part 2, I will be talking about randomized Byzantine Agreement, namely the classic framework of Michael Rabin and Michael Benoit. And then part 3, we will go technical and see how the randomized Byzantine Agreement problem reduces to another nice cryptographic primitive called as verifiable secret sharing. And if time permits, I will discuss some of my works in this part 3. So let's start with part 1. So the year was 1982, and these 3 wise chaps introduced a problem called as Byzantine general problems, published in a well-known A-star journal in system science. So I have highlighted Leslie Lamport in a color. So it's a trivia for you to find out who exactly is Leslie Lamport. And they gave non-computer science motivation for this problem, why they call it as Byzantine generals problem. So the problem description is the following. You have n generals. In this case, we have 4 generals. Each of the general is controlling one troop. And the generals are connected by pairwise private and authentic channels. That means they can communicate over the channels if they want to with any other general. And they have surrounded the enemy city. And each general has a secret plan, which you can call it as a bit. 0 means retreat, don't attack. 1 means we want to attack. And the individual bits of the generals are known only to the general at the beginning. And it's known that up to T of the generals may be traitor. That the number T is known, but it's not known who exactly are those T traitors could be. And the plan is to come up with an algorithm or a protocol according to which the generals should exchange messages with each other, talk to each other, so that finally all the honest generals or the good generals should have a common plan, whether to collectively attack or whether to collectively retreat, because the maximum damage to the enemy can happen only when all the good generals coordinate properly and have the same action plan. It should not happen that one good general comes under the impression that he has to attack, whereas the other good general decides, no, I am going to retreat. That should not happen. Yes, N and T are known a priori. And to make the problem more interesting, right, the requirement is that the final action plan, namely the final output bit, should be equal to the action plan of all the good generals if they all started with a common action plan. That means to begin with, if all the good generals were on the same page, we want that the output should be that same thing or the same input bit which they started. So this is the motivation. This is of course a non-computer science motivation, right? Why a computer scientist will be interested to solve such kind of problem. So now let's see some computer science abstraction of the same problem. So let me replace those replace those 4 generals or n number of generals by n number of systems or parties or computers, and they are mutually distrusting parties. They do not trust each other, and the distrust in the system is modeled by a centralized adversary or a bad guy, and we assume that at most t of the n parties could be bad. Which t we don't know, it's just a parameter, and the goal is to design a distributed protocol allowing the honest parties to agree on a common output. That's why the term agreement. And why it is called Byzantine Agreement, because in the last picture when they gave the motivation, they said this is the Byzantine Empire surrounded by n number of generals. Right? So people who don't know what is Byzantine Empire, just search in the Google. It's an ancient name for Roman Empire. Right? So Byzantine corruption means T of the bad parties, they can misbehave in any arbitrary manner. They may not follow the protocol instructions at all. They may send wrong values. They may send conflicting information. They may decide not to communicate. They are allowed to behave in any arbitrary fashion and deviate from the so-called protocol instructions. So what are the goals of the so-called protocol that we want to design? So you can imagine that the inputs of the parties are m sub 1, m sub 2 up to m sub n. They could be bits or messages from a bigger domain. The requirements are, the first requirement, that after the protocol terminates, that means once the parties exchange messages as per the protocol instruction, all the good parties should be on the same page in terms of output. They should output the same M. That's the agreement requirement. The second requirement is that if all the good parties started with the same input, then that should be the final output. That means the agreement, if at all it was there at the beginning of the protocol itself, it should not be disturbed. That's the validity requirement, and that makes the whole problem description very interesting, because if I don't put the validity requirement, then agreeing on something is very trivial. You just output a predefined output. It's a validity requirement which makes the problem very interesting. That means even without knowing which honest party or which party have what kind of input, your protocol should ensure that at the end, the output, the final output of the honest party should be the same input if they all started with the same input. So these are the two major requirements. So now you might be wondering where exactly we use such kind of protocols. Are they just theoretical abstraction? Well, they have lots of applications. The first application is what we call as secure multi-party computation. So if we have a distributed protocol, and if in that protocol you have a sub-protocol where I require a party to send his input or his information consistently to all the participants in the network, then a simple strategy can be that he sends it to each party one by one by one. But if the sender is a bad guy, the party who is supposed to disperse or broadcast his message to everyone, if he is a bad sender, a bad guy, then he may send different version of his inputs to different parties. In that case, we need a Byzantine Agreement protocol among the receivers to decide or agree upon what exactly is the common message that sender wants to send to them. So that's one of the applications. Another classic application is what we call as state machine replication or distributed databases. So the way typical distributed database operates is that it's not the case that the database copy is just maintained at one location. Because it's a very critical database, they maintain multiple replicas of the database. And imagine that the database is dynamic. In the sense, it has records of several transactions, and the transactions keep on getting updated and updated and updated. That means you can imagine that such kind of dynamic database operates as a sequence of time epochs, where in every time frame, you can imagine that various users who want to use the distributed database multicast various kind of transactions. Again, that transaction I'm considering at a very abstract level. It could be financial transaction, or it could be transaction related to supply chain management, anything. So imagine that the users of the system, they multicast transactions to the different copies of the database. And as a result, what can happen is that now each copy of the database might get updated. Since you want to ensure that after every time frame, that means from the current time frame and before the next time frame starts, before we go to the next time frame, all the good copies should be updated identically. So once the copies of the database, they get updated locally, what you want here is run a protocol, a Byzantine Agreement protocol, where it should be ensured that even if some of the components or some of the replicas got corrupted, still the good copies should come to the same page, and get updated to the up-to-date content. So that's how most of the real-world distributed databases are run, and they run the Byzantine Agreement protocol. Of course, not in its crude form. They do optimizations, but beneath any distributed database, you have the core component of any distributed database is a agreement or consensus protocol, which ensures that all the replicas after every time frame should be on the same page, even if some of the components get corrupt and start malfunctioning. So is the problem description clear? Right? So now it turns out that this Byzantine Agreement problem or distributed consensus problem has been studied ever since 1982 in varieties of settings. It's not that we just have a single setting in which we have formulated the problem and we came up with a solution. And it's not only studied just by the distributed computing community, it has been widely studied by the cryptographic community as well. Typically, when it comes to cryptography, people think that cryptographers are only interested in solving the problem of secure communication. Well, that's not true. We do a lot of interesting things, and this is one of the problems which kind of lies in the intersection of both cryptography as well as distributed computing. And you can see any of the theoretical computer science flagship avenues like POTC, Talk, Fox, or journals like Journal of the ACM Distributed Computing. You will find tons of papers, plenty of nice works dedicated to solving Byzantine Agreement problem. So some of the widely studied settings in which the Byzantine Agreement problem has been studied are as follows. So we can classify the problem depending upon the level of synchronization which is available among the parties or the n participants. So the participants may be completely synchronous in the sense that we can assume that in my network there is a global clock and we know when exactly 1 hour starts, 2 hour starts, and so on. Or we can assume that the network is completely asynchronous. That means each party has its own local clock. So that's one kind of division. Or you can have an intermediate, namely you can assume that a network is synchronous to begin with, and after some period of time it becomes completely asynchronous, and the situation may become completely chaotic. So that's one level of one dimension in which you can study the BA problem. Now, depending upon the type of faults, you can have crash faults. So they are benign form of failures, where the T bad guys, the only harm that they can cause is they can just crash anytime during the execution of the protocol. You don't know well in advance when they are going to crash. But as per the modeling, we assume that they can crash at any time during the execution of the protocol. But once they crash, they cannot become alive. That's a crash model. Whereas the more powerful adversary is the malicious adversary or the Byzantine adversary, which can capture any kind of bad behavior that you can think of. They can crash. After crashing, they can come alive. If they are alive, they may not follow the protocol instructions. If they are supposed to send a value 1 to everyone, to someone they may send 1, to someone may send 0, and so on. They can behave in any arbitrary fashion. That means those T-bad parties. Now, depending upon the setup available, so if we assume that some kind of cryptographic setup is available, and if we assume that the T-bad guys, they are computationally bounded, they do not have infinite number of resources, then we can use very fancy cryptographic tools like encryption, decryption, signature schemes to solve the problem. But if we do not want to make any assumption whatsoever about the computational power of the adversary, that means we assume that those T-bad guys may have access to any kind of computing resources, then the problem becomes more challenging. In that case, we go or demand information theoretic secrecy or information theoretic security. And depending upon the type of channels which are available among the parties, we can have private and authentic channel model where we assume that my underlying network is a complete graph where there is a direct link between every pair of parties. That's a complete network model. Or we can just assume that we have no access to private links between the parties. That means the adversary or the bad guys, it can see what everyone is communicating to everyone else. That means we just have the guarantee of authentic channels available between the parties, right? And you can see that the difficulty level of the problem goes from top to bottom, right? In terms of synchronization, if I want to design a protocol in the completely asynchronous environment, that will be most challenging. In the same way, if I want to tolerate a Byzantine adversary, that's more challenging than designing a protocol where your goal is to just handle crash failure. In the same way, if I am not allowed to use cryptography, then my life becomes more difficult, because cryptography gives you the leverage of using encryption, decryption, signatures, so on. And if you are not given pairwise private channels, that means adversary can see what the good parties are communicating with each other, then again the problem becomes very difficult. So these are some of the dimensions. Of course, I can go to several other dimensions as well, but these are some of the interesting ones. Yes. 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 I'm going to come, because natural question is, can I design a protocol for all values of n and t? Of course not. There are well-known bounds. Of course, Srikanth can tell about them, because once upon a time, this was his bread and butter. Many people don't know that some of the classic works in this area of fault-tolerant distributed computing has been done by our own Professor T.K. Srikanth. So, some of the known results, of course, I won't be citing your results in this case. So known results in the synchronous setting. So synchronous setting means it's a means you have the flexibility here. That means we assume that all the parties are synchronized by a global clock. And since there is a global clock, that means any algorithm or any distributed protocol designed in the synchronous model, it will execute as a sequence of rounds, right? Where in each round, the actions of the parties will be, I compute something, I sent it over my outgoing channels, and in that round, whatever the other parties have computed and sent to me, I will receive. So that means you can imagine that the protocol operates as a sequence of compute, send, receive, compute, send, receive. So if I say I have a 10-round protocol, that means you have 10 such sequence of compute, send, receive for every party. And since we are in the synchronous model, the advantage that we have is that the channel between every two parties, they have a fixed known delay, which will be known to everyone. Say delta. It could be 1 hour, 2 hour, or anything as specified by your system. Now the advantage in the synchronous model is, since everyone knows the delay that is there over every channel, then any expected message which you don't receive as a receiver within that period delta, you know that the sender party is a bad guy. And you can simply throw it away from the protocol for the remaining part of your protocol execution. That means not sending a message which a party is supposed to send in a synchronous model in a round is a very bad adversarial strategy. That simply reveals the identity of the bad sender. Because if say delta is equal to 1 hour, then I know that when I am going from 9th round to the 10th round, I have to maximum wait for 1 hour for every message to come to me. So within those 1 hour, whichever messages come to me, fine, you are a good guy, I believe so. If you don't send within those 1 hour, you are a bad guy. Kick him off the protocol for the remaining steps of the protocol. Yes.
What if you have where say in the 10th party is waiting for 1 hour and the 9th party, something has come to the 9th party. How do you know about the intermediate parties? One of them.
So we are assuming a direct channel between every pair of parties. Right, so that's an abstraction. Again, that direct link would be through intermediate nodes, but that's taken care in this abstraction. Right? So as coming to Professor Sridhar's question, for which values of t and n we can solve this problem? So first of all, the most trivial limitation on t and n is you cannot solve this problem in any setting if the number of corruptions become more than 50%. If you have n number of parties, you can never ever solve this problem if the number of bad guys outperforms the number of good guys. Okay, I won't go into the proof of this, but you have to believe me that this is the minimum bound, minimum relationship between t and n which you need to solve this problem. And interestingly, in a very nice work, Dolev and Strong, in their classic work published in Siam Journal of Computing, they actually showed that it's possible to design a protocol if you ensure in the system that t is less than n by 2. That means t less than n by 2 is kind of a necessary and sufficient condition for designing the protocol. Of course, the protocol that they gave requires enormous amount of communication, enormous number of messages to be exchanged among the participants. And this result of Dolev and Strong is under the assumption that you have a cryptographic setup available among the parties. That means you are allowed to use cryptography in your protocol. That means your bad guys are assumed to be computationally bounded, because cryptography simply fails if the bad guys are computationally unbounded. So this bound of t less than n by 2 is necessary, and it's sufficient as well if you are assuming your bad guys are computationally unbounded. Now, in the original 1982 paper where Lamport et al. Proposed this problem, they showed that if you are not assuming any PKI setup or cryptographic infrastructure, that means your bad guys are computationally unbounded, then you cannot solve this problem if you have more than 33% corruption. That means maximum 1/3 of the participants can be corrupt, and then only you can think of solving the problem. And they also presented inefficient protocols in the same paper. In fact, those protocols are called as exponential tree generation protocols because it generates a tree which has exponential number of levels, exponential in the number of participants. And then people started thinking about efficient protocols with t less than n over 3. And in a sequence of work involving Berman, Garay, Moses, they eventually ended up with getting polynomial time solutions satisfying the t less than n by 3 bound. That means we now also have efficient protocols tolerating t bad guys, where the t bad guys could be computationally unbounded and no cryptography is allowed in your system.
The assumption is that the bad guys remain bad guys throughout.
There may not be any bad guys. The assumption is you have to design a protocol which can tolerate any kind of t bad behaviors.
And the character of the
Okay, so you are saying yes. So you are saying no. So once they get corrupt, they get corrupt. Okay, so you are talking about a mobile adversary kind of thing, where say he is corrupt and gets identified, and in the meantime some another set of t bad guy. We have not studied that model. As far as my knowledge is concerned, no one has studied protocol in that model.
the efficient protocols still don't assume any unsigned cryptography.
Yes, so these works, they are in t less than n by 3. They are efficient without cryptography. And of course, we have efficient protocols with cryptography as well after the work of Dolev and Strong.
And one more question is, the Danforth paper assumes a basic communication setup is where you have to decide only between 0 and 1.
Okay, so I will come to that. Yes, I will come to that. I have a slide for that. Yes. So we assume here a centralized adversary who can decide what the t bad parties can think their input and participate in the protocol, whereas we have absolutely no assumption on the inputs of the good guys. So it's only the bad guys who work in coordination with each other. Now coming to asynchronous model, so these were all results in the synchronous model. So of course, whatever bounds we have, namely the relationship between t and n, they automatically carry to the asynchronous model. Because when you cannot solve the problem with these bounds of t and n in the synchronous model, of course you cannot solve the problem with with the bounds of t and n not satisfying them in the asynchronous model. So why the asynchronous model is very challenging? So internet is not synchronous. You don't know well in advance within how much time the message that a party has sent to you will come to you, right? So the challenge in the asynchronous model is if we have n parties and each party has its own local clock, then as a receiver, I cannot decide for how much time I have to wait for a message. It may come immediately, it may come after 1 hour, it may come after 2 hours, it may come after 3 hours, or what if the sender has not sent a message at all? That means in the asynchronous model, as a receiver, I cannot distinguish between a slow sender who is honest and a bad sender who has not sent a message, right? That means I can never write a asynchronous protocol where I have a step saying wait for all the n parties to send their messages to you. Because if you are waiting for messages from all the n parties, then the end may turn out to be endless waiting if the t bad guys decide not to communicate to you at all. And you cannot distinguish whether those t messages which are missing for you, whether they are going to come or not. That means the maximum you can afford is to wait for values from maximum n minus t parties at every step. And as soon as the messages from n minus t parties come, you immediately go to the next step of the protocol. But in this process, what may happen is you might be ignoring communication from t potentially good parties because you don't know what exactly is the status of those t missing messages. And to make the situation worse, if you have a 10-step protocol, the set of t parties from whom you are ignoring the communication, they may vary over these 10 steps. In the first step, I may be ignoring communication from one set of t parties and I have immediately proceeded to the second step. And in the second step, I might be ignoring communication from another set of T parties and so on. I cannot go back and say, oh, you have sent a message now, I should now do a different kind of action. You cannot design an asynchronous protocol like that. And that makes your asynchronous solving the BA problem in the asynchronous setting very, very challenging. So in fact, in the asynchronous setting, the assumption is that your network itself is the adversary. The adversary can schedule the messages, it has full control, and you still have to solve the problem taking care of that adversarial scheduling. So now, what are the known results in asynchronous setting? Right, so let me first redefine the problem, the Byzantine Agreement problem in the asynchronous setting. Again, our setting is we have a set of n parties, up to t of them are bad, and my network is completely asynchronous. And the goal is to design a distributed protocol satisfying the following properties. The first requirement, agreement, that means when the good parties terminate the protocol, they should have the same output. That's the agreement property. Validity remains as it is. That means if all the good parties started the protocol with the same input, then that should be the final output. And now comes the challenging part, termination. You have to design your protocol in such a way that irrespective of how the scheduling happens during the execution of the protocol, the good parties should eventually terminate the protocol. So the guarantee that is given in the asynchronous model is, even though the messages may get arbitrarily delayed, a message sent by an honest sender will eventually be delivered to the receiver. You are given only the guarantee of eventual delivery of the messages. It won't be the case that the messages will be kind of indefinitely not allowed to go delivered to the receiver. It will eventually be delivered to the receiver, but when exactly that eventually happen, we have absolutely no assumption whatsoever. So now the termination requires that your protocol should ensure that eventually all the honest parties should terminate the protocol and have some output. Now, what are the known results in asynchronous Byzantine agreement? So it's known that irrespective of whether cryptographic setup is allowed in the system or not, you cannot solve the problem in the asynchronous environment if t is more than n by 3. That means in the synchronous setting, right, if you see the two charts on your right hand side, in the synchronous setting you have the difference between the threshold. If cryptography allowed, you can tolerate up to 49% corruption. If cryptography not allowed, you can tolerate only 33% corruption. But in the asynchronous environment, it's well known that it doesn't matter whether cryptography is allowed, not allowed. You cannot design a protocol solving asynchronous Byzantine agreement tolerating more than 33% corruption, and the proof is very simple. Imagine I try to design a protocol with n equal to 3 and t equal to 1 for the moment. That means I have 3 parties connected by asynchronous channels, and up to one of them could be bad. You can imagine a scenario where you have 3 parties, say A, B, C, and say A and B, B and C are good. And what this adversary can do is, since it's an asynchronous network, it can prevent communication from B to C happening. That means it can keep on delaying messages from B to C and from C to B. And it can only communicate incorrectly towards A and give the impression that I have my input 0. And in the same way, it can give A is the bad guy here, and it can give an impression to C that my input is 1, which ensures that B and C ends up outputting different things, because the communication between B and C keeps on getting delayed arbitrarily. That's a rough intuition that why you cannot solve the problem with one corruption among 3 parties. As they are allowed to communicate, but as per my network modeling, the adversary A has the control over scheduling of the messages.
So even if the adversary A is bounded and can communicate, B and C can,
okay,
still C cannot decide, for example, if the exchange knows as to what he said. C cannot decide whether B or A is the adversary.
Yes, of course. So you consider this scenario with another scenario where in the protocol, say B was the bad guy. Indeed, B is the bad guy, and A was honest. In this case, C had to decide based on the messages just it sees from A. What now A is doing, we have now a different execution where A is bad and he has created an impression for C that actually B is the bad guy. So whatever C could do in this execution, the same thing C would have done in the honest execution. And that's why you cannot solve the problem with 3 parties and 1 corruption. And this generalizes to the case when n is equal to 3t and up to t of them are bad. Because basically you have 3 partitions and the 2 good nodes, their exchange of messages are delayed arbitrarily, and it's a bad guy who is kind of giving inconsistent views to the 2 good guys. And this will hold irrespective of whether cryptography is allowed or not allowed. Right? Now comes the interesting part. So in 1985, yes.
Proper if you have say A and C and C not communicating, they will eventually be allowed to communicate.
No. So in my protocol instruction, B can wait only for messages from maximum 1 other party, apart from his own messages. Because T is equal to 1, so as per my protocol instruction, I cannot wait for all the 2 other parties to send to me. So taking advantage of that, what adversary can do is it can delay the messages of C arbitrarily and give the B impression that actually C is the bad guy. Now, in 1985, Fisher, Lynch and Patterson gave a warning. It gave a warning to the system guy that don't ever dare to design a deterministic protocol in the asynchronous environment to solve the Byzantine Agreement problem. What they prove is that irrespective of what protocol you design, using cryptography, not non-cryptography, it doesn't matter what are the steps in your protocol, there always exists an adversarial strategy where adversary can just crash one party and it will ensure that your algorithm keeps on running forever for the good parties. Irrespective of what is allowed in your protocol step. You can use any kind of protocol, there always exist non-terminating executions, and they were later on awarded the Dijkstra Prize for distributed computing, which is kind of considered as the highest recognition in the distributed computing community. Right? So I'm not going into the proof of this. Probably Professor Srisha Rao talks about the FLP impossibility result in his distributed computing course. So you should attend his course if you want to learn the proof of this. It's really a very nice proof. So now the question is, if FLP have proved that you cannot design an asynchronous protocol, because if you try to design an asynchronous protocol, adversary can always cause your protocol not to terminate. Does that mean that we cannot define or design asynchronous protocol? Because in reality, we will require an asynchronous protocol because internet is asynchronous. It's very, very difficult to ensure synchrony in the network. Well, the answer is no, because if you see the statement of FLP, they say that deterministic protocols have non-terminating executions. What you can do is you can embrace randomness. That means you can now design randomized protocols, where by randomized protocols I mean that as part of the protocol steps you can make random decisions. And the credit for starting this whole area of randomized protocols, it's attributed to Michael Benor and simultaneously to Michael Rabin, who along the same time started this whole work, research of randomized agreement. And of course we have Gabriel Bracha also doing some pioneer work in this area. Sorry, I couldn't get his picture, that's why it's a question mark. Probably Professor Shrikant can give, because I was told that he was his batchmate when he was doing PhD. So I can take pictures. Yeah, so but you might be having the picture. I can put it in my future talks. Right? And they defined 2 types of asynchronous agreement protocols, because now we are talking about randomized protocols. And randomized protocols means it's not necessary that they will always terminate. There is always some error in the termination. That means you might be now expecting for termination guarantee with high probability. So we have 2 classes of randomized protocol. The first class is 1 minus lambda terminating, which ensures that all the good parties, even if it's an asynchronous protocol, terminates except with probability lambda, where lambda is some parameter which you can set as part of your protocol specification. And we have another class of randomized protocols where it is ensured that all the good parties terminate with probability 1. and they are called as almost surely terminating. Now many people feel that termination with probability 1 means always terminating. No, because remember, it's a probabilistic termination guarantee. What almost surely terminating means is you keep on running the protocol forever, asymptotically it will eventually terminate. Whereas 1 minus lambda terminating means there is some proportion of randomness, namely lambda proportion of the randomness, for which the parties may not terminate your protocol. So these are the two classes of randomized protocols, and they showed that indeed by doing randomness we can circumvent the FLP impossibility result. Notice that I am not saying we are avoiding the FLP impossibility result still holds for both these classes of protocol, because once you fix the randomness in your protocol, it becomes a deterministic protocol, right? So what this class of randomized protocol says is it gives you the guarantees of terminating with high probability.
What aspect of the protocol is deterministic?
We will come to that, how exactly randomness is coming into picture. Right? Now coming to your question, right, from binary agreement to agreement for any domain. So till now I was considering Byzantine agreement problem where I said that messages could be from any domain. And you have another version of the Byzantine agreement problem where the inputs are just bit, namely the Byzantine generals problem, where the inputs of each party was just a bit. So you have two different versions of the problem, and it turns out we have a line of research which says how to do the domain extension. In the sense, if you give me a Byzantine agreement protocol in some setting for the binary version, I can apply the domain extension. They are generic in nature, and that gives me Byzantine agreement problem where the domain could be anything. And we have a series of very nice interesting work which does the domain extension itself, including some of my own work. So we have these results. So that's why for the rest of the talk I will focus on the binary agreement problem, because assuming you have a binary agreement problem, you can apply any of the so-called domain extension results and get the agreement problem for any domain. So coming back to the roadmap, the test match is over. I have introduced the problem, what are the known results, FLP impossibility result, and the randomized protocols. Now let's see how exactly randomization helps us to circumvent the FLP impossibility result. So this is the part 2. So on a very high level, what Rabin and Benor said is the following. Imagine you have two protocols, two sub-protocols, two gadgets. The first gadget is a voting protocol, and it's a 3 rounds of asynchronous interaction, and it's a deterministic protocol. There is no randomization there in the voting protocol. What it does is, it allows the parties to participate with their input, and then they agree messages with each other 3 times, and then they make a decision. And the output of this voting protocol for each party is a bit along with a grade, and the grade could be sure, not sure, no idea. We will come to that, what exactly it means, what exactly is the interpretation of a grade being sure and a grade being not sure and a grade being no idea. But the bottom line here is it's a completely deterministic protocol, asynchronous protocol, and it helps you to solve the agreement problem just using deterministic message exchanges. And the second component, you can imagine that the parties have access to a Guruji, trusted Guruji, which I call as a common coin protocol. CC means common coin. So what this gadget does is, you imagine that the parties just shout, Babaji please come, Guruji please come, and the Guruji appears. He picks a bit for every party and gives the bits to the respective parties. And why it is called common coin? The guarantee here is that Babaji will guarantee for you, or the Guruji will guarantee for you, that with probability P sub B, the bit that he has chosen for all the honest parties will be same. Right? So P0 means with probability P0, it will be ensured that Guruji has selected the bit 0 for all the good parties. And probability P sub 1 means the Guruji has ensured that all the good parties are getting the bit 1. And P0 and P1 will be known as part of the system specification. For the moment, assume such a Guruji exists, such a sub-gadget exists. And this is a randomized component in the overall framework. What Rabin and Benor showed is that if somehow ensure that this P0 and P1 are constant, say for instance 1 over 4, then by composing these two gadgets, for 17 number of times, you can actually solve the Byzantine Agreement problem. How the composition happens, we will see that. But that's the overall idea, right? So let's see what exactly is the vote protocol all about. So as I said, it's a deterministic protocol where parties just exchange their inputs during the first round. And then during the second round, they exchange among each other what are the n-2 votes that I have received from the other parties. And then in the third round, they again say what are the set of n-d votes that they have exchanged in the second round. And then they take a decision. So it's a completely deterministic message exchanging. And as I said, that the output for each party is a bit and a grade. Now, what are the interpretations of the grade and what are the properties of this vote protocol? Interestingly, this vote protocol ensures that if all the honest parties started with the same input, then they will agree on that same output. Then they will agree on that input. That means the output for all the parties will be the same bit B and the grade equal to sure. And the grade equal to sure means it's an indication for the party that we have an overwhelming majority for that bit B. That's the most important part of this vote protocol. Remaining two possible outcomes could be that if some honest party outputs an output B comma sure, that means he has output a bit B and his grade is sure for that bit B, then your vote protocol ensures that every other honest party are also going to output B comma sure. That means they won't output B complement. They will output either B comma sure or the bit B comma not sure. But they won't output B complement. That's the second property your vote protocol guarantees. And forget about this complicated third property. That we are not going to use. So pictorially, we can imagine that the outputs of the parties are going to be just a bit, either 0 or 1, and along with that, a tag for that bit. Sure, not sure, and no idea. So sure and not sure are good outputs because you can feel that, okay, either there is an overwhelming majority or high majority or distinct majority, whereas if the output is kind of question mark with not sure, then you don't know what exactly is happening here. No, it's just, okay, the name is confusing here. You can call it as any fancy name. It's just pure message exchange of messages, that's all.
So the voting is done, and after the voting is done, it is based on just simple majority.
Yes, majority definition. Yes, so it's n equal to 3t plus 1. Imagine I wait for 2t plus 1 messages during first round, again do the communication, wait for 2t plus 1 messages, and then I take a majority and output something. That's all. And based on that, I output sure, not sure, no idea. Now let's see how we can compose these two gadgets, a voting protocol and the Guruji protocol, to get a randomized BA. Can we take it out because I am running out of time? I can give you the proof for that, right? So here is how the two gadgets are getting composed. So the protocol is going to be operated at a sequence of iterations. And in each iteration, the parties are just going to perform the same set of tasks. They start with their respective inputs, and then they run the voting protocol. And after their voting protocol, they will have some bit and a grade for that. And then they call the Guruji, please give us coin. And the Guruji is called irrespective of what's the output of your voting protocol. Now what you do is, if you are a party where the voting protocol has not given you any indication what exactly is happening, you take the output, the coin that the Guruji has given to you. But if your voting protocol has ensured for you that you got a bit with either the grade sure and high confidence, then you stick to that bit. You don't take the bit of the Guruji. And then you again repeat. And of course, you have to do some extra bookkeeping, but this is the high level idea. In each iteration, run the voting protocol and then independently call the Guruji. If the output of your voting protocol is good enough, which gives you an indication that agreement is about to be reached, that means the grade is sure and high confidence, stick to that, don't change your bit. But if you are not sure with respect to your output of your vote protocol, take the bit that Guruji is giving to you. And then you go to the next iteration. The idea here is, in each iteration, there could be two possible cases. The parties, if all the parties start with the same input in any iteration, imagine in some iteration, all the good parties start with the same input, then the vote protocol itself suffices to lead them to an agreement. You don't take the output of the Guruji. The problematic case is only when all the good parties don't have an agreement to begin with. They have a mixed bag of inputs. Only in that case, you have to analyze what's the probability that the coin that Guruji is going to give to you not matches with the output that other parties have used while setting or while taking the output of the vote protocol as the input for the next iteration. Right? So, if the coin which Guruji is giving to you matches the output of the vote protocol for the other parties, that means when you go to the next iteration, immediately the vote protocol will settle the agreement. The only problematic case could be when the coin which Guruji is giving to you does not matches with the output of the vote protocol for the other honest parties. In that case, when I again go to the next iteration, it's as good as saying that the good parties have a mixed bag of inputs, and again they have to repeat this process, and then they have to hope that the next time when they are calling the Guruji, this disagreement kind of resolves. So now you can see that why this is an almost surely terminating protocol. Because in the worst case, what may happen is that in each iteration, the coin that Guruji is giving to you might mismatch with the output of the vote protocol for the other honest parties. And this may keep on going forever. What is the probability that this won't go forever if you run these iterations for k number of times? Well, if your P0 and P1 are constant, say 1 by 4, then the probability that this keeps on happening for k number of iteration is 1 minus 3 over 4 raised to power k, which becomes almost 0 if you keep on repeating this for infinite number of times. That's the whole idea. Now the whole problem boils down to how do you instantiate this Guruji? Because we are in Kali Yuga, right? We don't have access to such trusted Gurujis. If we are in Satyuga, then we can imagine that we have access to such Gurujis. And if we would have been in Satyuga, then we don't need cryptography at all. So what Rabin and Benor said is, if you give me this trusted Guruji, who has this property that with probability P0, all the good parties will be outputting 0, and with probability P1, all the good parties will be outputting 1, we don't have to do anything extra, just keep on doing it. The agreement will achieve. So now the goal is, we have to emulate the role of this trusted Guruji by running a protocol among the participants themselves. Right? So we assume that apart from the channels, parties don't have access to any other resource. So now the question boils down to how do you emulate that goal, the role of this trusted third party. Now depending upon whether your Guruji that you are emulating by running a protocol, what kind of protocol it is. If it is 1 minus lambda terminating, then your overall agreement protocol becomes 1 minus lambda terminating. That means if you design a coin protocol which may not terminate except with probability lambda, then your overall agreement problem is 1 minus lambda terminating ABA protocol. Whereas if it is ensured that the coin protocol that you have designed, where the parties exchange messages with each other, always terminates, then this framework is going to give you an almost surely terminating protocol. So the whole problem now boils down to what type of coin protocol you are going to design. So that's part 2. On a very high level, the framework of Rabin and Benor, the randomized protocol, randomized agreement protocol. Now we will see that how exactly we go about designing the coin protocol. Right? So before going into that, some genealogy of what exactly are the important results in context of randomized ABA protocols. So what I am going to show is various results which have appeared over a period of 30 years, and the resources based on which I compare the protocols are resilience, namely how much fraction of the bad parties you can tolerate in that protocol, expected communication complexity, that means how much bits are communicated by the parties in that protocol, how many steps or the number of iterations you have to do in that protocol, and the amount of computation that is involved by the parties in that protocol. And I will be just comparing the randomized asynchronous protocols here, of course. So as I said, Benor started the whole line of this asynchronous agreement protocols. His protocol definitely has a very bad resilience. Ideally, you should tolerate up to 33% corruption, but he could tolerate it, his protocol could tolerate only 1/5 of the corruption. And the worst part is the coin protocol, its running time was exponential in the number of parties. Then Bracha improved this result. He improved the result to t less than n over 3, that means optimal resilience. But the coin protocol has exponential expected running time, expected exponential amount of communication, and then a history was made by a classic work by Turing Award winner Silvio Micali and his student, who gave a polynomial expected running time coin protocol. In fact, the expected running time was constant. You just have to run that iteration constant number of times. And the communication complexity was also polynomial, n to the power 6 log times the size of finite field. So f is the size of field over which all the computations are performed. But the bad side was it's not optimal resilience. Ideally, you should tolerate up to 33% corruption, but it could tolerate only 25% corruption. But that was the kind of a landmark result. Then in 1993, Kennedy and Ribin, they gave another kind of coin protocol, which is not always terminating. It's 1 minus lambda terminating, but it achieves optimal resilience, t less than n by 3, and polynomial communication and computation. Then in POTC 2008, Abraham, Dolev, and Halpern, they actually came up with the first protocol, which is almost surely terminating. That means coin always terminates. Optimal resilience, t less than n over 3, and expected polynomial computation and communication. Then in POTC 12, myself and my colleague, we improved the protocol of Kennedy-Ribin. So we still couldn't get a almost surely terminating version. Our protocol was 1 minus lambda terminating, but we improved the communication complexity of Kennedy and Ribin. And then there was an unpublished manuscript which gave an almost surely terminating coin protocol, optimal resilience, but involved exponential amount of computation from the parties. And then last year, myself and my IM Tech thesis student and my colleague from ISC, we gave the first polynomial time solution, optimal resilience, and we improved the expected running time of the protocol of Halpern and Dolev and Abraham. So now this is the best known protocol in terms of almost surely termination. And now the obvious question is what lies ahead of this. So I will come to that in the conclusion section. So these are the important results. So now how exactly we go about designing the coin protocol. So now I will slightly rush here. So the main tool that we do or that we use in designing the coin protocol is what we call as secret sharing, verifiable secret sharing. So the problem description is the following. So it's again another interesting cryptographic primitive. We have a set of n parties. We have a dealer who has a secret which it wants to share by giving a share to each shareholder. And the shares should be distributed in such a way that if any t of the n shareholders come together and pool their shares, they learn absolutely no information about the secret. But if t plus 1 or more number of shareholders come together, they should be able to reconstruct back the secret. So here t is your threshold. Any number of shares up to t, no access to the secret. Any number of shares from t plus 1 or more, secret should be reconstructible. And Adi Shamir, the S of RSA fame, he gave a very, very clever, nice solution for this. In fact, it's one of my personal favorites, simply based on higher school mathematics. It does not involve any complicated things. So here is how you can distribute the secret. Imagine your secret lies in some finite field. To share it, you pick a random polynomial, say f of x over the field, where the coefficients of the polynomial are totally random except the constant term. That means it's the constant of the polynomial which is the secret, and then you just evaluate this secret at n known values. That means the first party, he gets the share which is nothing but the value of this unknown polynomial evaluated at x equal to x1. The second party, his share is nothing but the value of this unknown polynomial at x equal to x2. And like that, value of the share of the nth party is nothing but the value of that unknown polynomial at x equal to xn. Why this works? If any t plus 1 parties come up with their shares, they are coming up with t plus 1 distinct values on a polynomial of degree t. For instance, if t is equal to 1, we know that two lines on an x, y plane uniquely define the straight line which dealer might have picked. But if only one shareholder tried to reconstruct the secret which was shared by the dealer, it could be any straight line over the x comma y plane. Simple high school mathematics. Right? So Samir's secret sharing, it works against a semi-honest setting. Namely, it will serve its properties as long as the T bad guys follow the protocol instructions properly, but it won't be secure if you go to the malicious model, where in the malicious model, the T bad parties could deviate in any arbitrary fashion. So there are two potential problems. Case one, if you have an arbitrary long bit string, map them to individual field elements and do this instance of secret sharing for each of the field elements. So what we are basically doing is we are mapping an arbitrary long bit string to the finite field elements. The reason we are doing finite field arithmetic here is that we cannot get security guarantees if you do arithmetic over integers. And second reason is your computation will be error prone if you don't do the computation over finite field. Rather you do the computation over reals or integers. Case one, where this protocol will fail is if the dealer is honest, but at the time of reconstruction, the shareholders, they just give you bogus shares. It turns out that Shamir sharing is nothing but an instance of a Reed-Solomon error correction, which coding theory experts, McEllis and Servete, noticed long time back. They said that it's very simple to deal with the case of bad shareholders, because what you have to do is just pure Reed-Solomon error correction, because Samir's secret sharing is nothing but a special instance of Reed-Solomon error correction. The second case could be where this protocol might fail, this Samir's secret sharing, is where the dealer itself is bad and he may not pick a t-degree polynomial. So remember, the protocol code is that the dealer should pick a t-degree polynomial and the shares should be the points on that t-degree polynomial. But if the dealer is bad, he may pick an arbitrary degree polynomial, distribute shares on that arbitrary degree polynomial. What verifiable secret sharing does for you is that it gives you a guarantee that even the potentially bad dealer has indeed used a t-degree polynomial and given points on a t-degree polynomial. That's why the name verifiable secret sharing. And this verifiable secret sharing we have to run in the asynchronous environment if we want to design a coin protocol in the asynchronous environment. And it has three requirements. Secrecy means any number of T shareholders, they should not learn about the secret if the dealer is honest. Correctness means even if the dealer is potentially bad, he should stick to a single t-degree polynomial and distribute points on that t-degree polynomial. And termination requirements, because we are in the asynchronous world, we need that all the good guys should eventually terminate. So remember when I showed you the existing result, there was one kind of breakthrough result, the Silvio-Micali and Feldman result. What they showed is, if you want to design a coin protocol, you just have to have an asynchronous verifiable secret sharing protocol. You give me an asynchronous verifiable secret sharing protocol, I tell you how to get a coin protocol. That framework is a very, very nice algorithmic technique. But that reduction from the coin to the secret sharing works only for the case when T is less than n over 4. But we are interested to design a coin protocol tolerating T less than n over 3 corruptions, namely the optimal number of corruptions. Our framework and the framework of Abraham et al. And the unpublished manuscript, what we do is, instead of designing a coin protocol, we design what we call as a shunning common coin protocol, a shunning variant of the coin protocol. And what exactly is this notion of shunning? You can imagine that a shunning protocol is kind of a pessimistic approach. A guy who always think about the worst possible thing, that adversary will always strike, he will always do nasty things in your protocol. And if you try to design a protocol where you have a pessimistic approach, then you will end up making your protocol complicated, trying to achieve all the properties even against the worst possible adversarial scenario. That means you are always thinking of the worst that the adversary can do. That's a pessimistic approach or of designing a regular protocol. What I mean by a shunning protocol is that you become optimistic. That means you don't worry that adversary is going to strike or not. That means if your goal is to design a protocol which should achieve m number of properties, you do not give the guarantees that all the m properties will be satisfied. Some of the properties will be definitely achievable and some of the properties may not be achievable. But those properties will not be achievable if only the bad guys strike. That means they deviate from the protocol. But if they deviate from the protocol, you still give the guarantee that you have some kind of detection mechanism where the good guys end up identifying some bad guys, so that those bad guys are kicked off for the later executions of the same protocol. So remember, in the framework of Rabin and Benor, we keep on running the coin protocol again and again and again. If in some iteration the coin protocol fails, the shunning guarantee gives you the guarantee that at least one good guy will kick off one bad guy, and when the next iteration starts, communication from that bad guy will be shunned off. So what the bad guy can do is, he may keep on doing it again and again and again, but after n square number of failed iterations. Why n square? Because there could be t number of bad guys and n minus t number of good guys. And in the worst, what may happen is, for each failed instance, one new conflict comes, and after t into n minus t number of conflicts, your system will only have good number of participants, honest participants. And then you will have only clean executions, and as soon as you go to a scenario where you have a clean executions, the protocol will achieve all the properties that you expected from your optimistic approach Pala protocol. That's the whole idea, so I'm skipping through it. I don't have time for that. So let me come to the conclusion and open problems. We discussed about asynchronous agreement problem, a fundamental problem in distributed computing, and there are plenty of challenging open problems. First, the most important one is, can we get a constant expected running time coin protocol with optimal resilience? The work of Micali and Feldman does it, but with t less than n over 4, we want a polytime solution where the expected running time of the coin protocol is constant and with optimal resilience. Of course, improving the efficiency, the communication efficiency of ABA protocols is a big challenging problem. We don't have any kind of lower bound results. And the most strongest adversarial model that you can think of is asynchronous Byzantine agreement in the so-called full information model. And what is the full information model is, we assume here that the adversary is computationally unbounded. That means no cryptography allowed. And we assume that parties don't have any kind of pairwise secure channels. That means we assume that anything communicated between two honest guys, adversary could completely see it. The only thing he can't do is, he can't predict the future coin tosses of the good guys, because he don't have access to the code of the good guys. And apparently we don't have too many works in this stronger adversarial models. Whatever protocols we have, their resilience is very poor, of the order t less than n over 100 kind of bound, and the communication complexity are very, very poor, because the model here is very, very challenging. With that, I thank the organizers for arranging this nice thematic cryptography based Samvaad series. Thank you.